Hey folks, how's it going? This is Mr. Murray coming to you with a little video based on the Unit 5 review, Course 2 Honors. Um, in this video, I'm going to briefly shoot through some of the packet, ideally not the whole thing, but some of it to explain some of the concepts that are going to be coming up on the tests. All right, here we are. And, hopefully this will answer some of the questions you might have. In advance, I hope you'll forgive any noise my computer's making right now. I'm actually in the process of churning out another video as we talk, and that video is going to be up pretty soon about proportionality and right triangles and the geometric means. Okay, so on this test coming up, here's the main focuses. So this unit is about similarity, right? Last year we talked about congruence. This year it's about similarity. Now, just like in middle school, you also talked about maybe similarity, but we're looking at it on a little bit more advanced level this year, okay, than you might have done in middle school. Just like how in ninth grade we looked at similarity on a more advanced, or rather, ninth grade we looked at congruence on a more advanced level than you looked at congruence in eighth grade, okay? So the topics that we're going to talk about are dilations, the transformation, fundamentals of similarity, the theorems of similarity, the triangle proportionality theorem, using proportional relationships, proportionality in right triangles and geometric means, and finally, context. Okay? So I'm using these, and notice that I did add a another pepper here, the Carolina Reaper, as a super hot level of pepper for most of these, just to give us a little bit of additional practice there. Okay. Okay. So I'm going to move on to the first one. So here we go. To perform a dilation, okay, you need two things. You need a center. You need a point around which to dilate, and you need a scale factor. Okay? So the center of the dilation is the point where the points you're transforming are either exploding out from or being sucked into, right? If the scale factor is more than 1, everything's being shot out, and if it's between 0 and 1, it's being pulled in, okay? So if the scale factor is greater than 1, the figure should expand, and if it's between 0 and 1, it should contract. It should pull in, okay? If you can map a shape onto another shape using dilations, rotations, translations, and reflections, or at least a combination of them, the two shapes are said to be similar, okay? That was our introductory geometric definition of similarity, okay? So I'm going to show you some transformations, but not all of them. I'm going to show you one of them about the origin, and then I'm going to show you one of them about a non-origin point, okay? So what I have here is, we're going to look at my origin, and that's 0, 0. Okay, now if you zoom in here, sorry if there's any lag. So when I zoom in here, I need to go dilation by 2 about the origin. So this is 2 away from the origin, so now it becomes 4 away from the origin. Okay, so A was 0, 2. Nope, it was not. See, even as a 30-year-old adult, I still get that flipped around. 2, 0, A prime, 4, 0. Okay, B is negative 2, 2. So B prime, scale factor of 2, is negative 4, 4. Remember, the doubling trick only works, okay, because the center of dilation is 0, 0. Okay, so it doesn't always work. How I look at it is this. How far is C from the origin? Boom, boom. 2 of these jumps. So how far is it going to be when I do the dilation? Boom, boom. 2 more of these jumps, right? So now the distance here is between here and here, up 1 over 2, now up 2 over 4. Here it's up 1 over 3, up 2 over 6. See that? So everything has been doubled. Okay, if we want to look at C and C prime, C is, I believe, 4, 4, and here we have 8, 8. Okay, so that's an example of one about the dilation about the origin. Here they're going to be pulled in, so only going to be half as far away, and in C they're going to be 1.5 times as far away. I encourage you to reach out to me about that, but for time's sake I'm going to move on and look at one that's dilated, not about the origin. So I'm going to look at this first one, a dilation about 2, 0 with a scale factor of 1/2. So now look, I'm at 2, 0. What's going to happen to A? A is going to stay exactly where it is. It's 0 away from itself. It's going to remain 0 away. Okay? B. Now B, I've got to go up 1 and over 2. So now I'm going to go up 1/2 over, well, rather, I've got to go up, actually, technically 2 and over 4. So I'm going to go up 1 and over 2. Now C, I've got to go over 2, up 4. So I'm going to go over 2, up 2. And now I connect and observe that these two triangles are similar to one another, right? Just as we've always seen. So this is C prime, A prime, B prime, okay? So that's a little brief shot at similarity. Please feel free to rewind, go back, and look through anything I did again, particularly making sure you've got the bell peppers, and then in a moment I will move on. Alright, so the next topic we're going to talk about are fundamentals of similarity. Similar shapes always have proportional sides, and they've got congruent angles, okay? So, it's important to know how to write a similarity statement. I'll write a couple of these. So here, these triangles are similar. So, big triangle, R, P, Q is similar to, we've got to line it up with the similar ones. So I've got R is congruent to itself. That's how you line it up. S, we can see, is congruent to P. T is congruent to Q. So you line up the congruent angles. Okay? Here, I've got B, A, C. Doesn't matter what you really call the first one. And now B goes with E, A goes with D, C goes with F. So, do you have to do BAC and EDF? No. You could go ABC and DEF. You could go CAB and FDE. You could go CBA and FED. There's lots of ways to write it, lots of ways that are correct. All that matters is that the congruent angle at that letter is right, whatever, in essence, whatever angle is up at this letter needs to be congruent to whatever angle is up at the corresponding angle, because these angles have to be congruent. Okay, that's important. All right, so suppose the triangles are similar. Which of these is not true? So what I know, let's take a look, is ABC congruent to ADE? Yes, it is. A lines up with A, D lines up with B, C lines up with E. Now, is angle AED congruent to angle ACB? Yes, because the triangles are congruent, their corresponding angles are congruent, therefore those are corresponding angles, so they are congruent. Okay? Now, we have to take a look at a ratio here. Okay? This is not as easy. So, what we know, right, is that we have this, right? So, we have DE is to BC as AE is to AB. Now that is a little weird statement. DE is to BC, they're the bottoms. But while AE is the left-hand side of there, AB is not that. So this one I'm going to put on the possibility table. That something doesn't look right there. All right, and that could be because it's not the right thing. Okay. So now, is ABC congruent to ADE? Yes, they're corresponding. Is AD to DE as AB is to BC? Yes, they are, because not only is the fact that, right, so here's the thing with similarity. You have proportionality between corresponding sides, but also if I take the ratio of any side to another side in the same triangle, that ratio has to hold between the corresponding sides of the similar triangle. So for example, here's two similar triangles. The ratio of this side to this side is also equal to the ratio of this side to that side. So the statement that is not true is C. Okay, so that's just a little touching on it. You know, there are some good problems here about similarity. I encourage you to try them. But in a moment, I am going to go ahead, you know, take a look back if needed. But again, in a moment, I will move on just for time's sake to the next set of problems. All right, so similarity theorems. There are three similarity theorems. There is angle, angle. There is side, side, side. And there is two sides and an angle between them. Okay? So, angle, angle similarity looks like this. Suppose I've got two triangles and they have two pairs of congruent angles. They are similar by AA. Okay? Let's say I've got two triangles and they have 6 and 8. Okay? And this is 12 and 16. 6 is to 12 as 8, and let's say that this is 13 and this is I don't like 13. See, it's hard to make them up on the spot. Say this is 24 and this is 32. Right? Because 6 is 24 as 8 is 32. So these are proportional, right? 6 is half of 12, or 6 is to 8, right? This is 3/4, this is 3/4, this is 3/4. Okay, also half, half, half. Okay, finally, side angle side. So suppose we have a congruent angle and we have two, so we have two pairs of corresponding proportional sides, and the included or angle between is congruent. They are side angle side similar. Apologies about that. They're side angle side similar. Okay? So how do we use this? Well, let's see. Can we show that any of these are similar to each other? Well, notice that we have some similarity here. So let's see, actually, do we though? Because it's the angle in between the two sides. This is like ASS similarity, which is not a thing. Okay, so 12 is to 20. That's 3/5, 3/5. But no, because this is not between them. How about this? So this is 2/5 because they have a 5 in common. This is 3/5. This is divided by 5, 3/4. I would be inclined to believe no, these are not proportional. Finally, let's take a look at this one. So here's the trick. If this is 81, this is 60, right? Well, what does that mean? Well, this has to be 39 because I've got to add up to 180. Okay, similarly, well, 40 plus 81 is 121. 180 minus 121 is 59. So I don't have two pairs of congruent angles, so these are not similar either. So as it turns out, really, nothing's similar here. Nothing's really working out, right? These ones, right, the angle is not between the corresponding sides. So it's not going to work. It is here, but it's not here. Okay? So it's not going to work. Here, we have a 3/5, right? This is not working either. 3/5, 2/5, 3/4. Okay? And this one, we don't have the congruent angles. None of the angles are congruent. We can't show the sides are either. Right? So here, in this problem set, there's other ways to do some applications. All right? And that is cool as well. So please make sure you understood anything from here. Again, especially the green pepper notes. All right? These were in a handout in the 2019-2020 school year. This was handout 3-4. So my apologies. 3-4. Okay, so I'm going to go ahead and move on to the triangle proportionality theorem. So the triangle proportionality theorem says, okay, that if I divide a line, I draw a line that divides this, right? So it's through two sides of the triangle and it's parallel to the remaining side, then the lengths of the segments are proportional as follows. Segment AD is to BD, as segment AE is to segment CE. Okay, in other words, this segment is to this segment as this segment is to that segment. These are also proportional as well. This is to this and this is to that. There's lots of different proportionalities. Now, this is what we call a bidirectional statement, meaning the converse is also true. So the triangle proportionality theorem says that if I divide this line through it such that the lines are parallel, then I've got proportionality. On the other hand, if a line cuts through the two sides and the proportionality holds, then what we know is the line cutting through the triangle is parallel to the remaining side. So this statement says if parallel, there's proportionality. This statement says if there's proportionality, they're parallel. So that means that parallelism in this case is true precisely and at no other time than when you have proportionality. Okay, so I'll do a couple of examples here to help you get a sense of what's going on. So what I have here is I need to find x. So I know that because of this parallelism, 6 is to 2 as 9 is to x. So I've got, by multiplying 6x equals 18. So x is going to go ahead and be equal to 3. And notice 3 times 3 is 9. 3 times 2 is 6. Here, I've got 3x minus 5 is to 10. As 20 is to 8. I know this is 20 because the whole thing is 28. So I've got 200 equals 24x minus 40. So 240 equals 24x. So x equals 10. Okay, x is 10. Notice if I do that, I get 25. So 10 is to 25, that's 2.5. 8 is to 20, that's also 2.5. Okay, now, I'll make note this is x is 3 on this one. Now, why are these parallel? So we're thinking reverse. So notice, what is 6 over 18? Actually, we could do it easier this way. What is 18 over 6? It's equal to 3. What's 24 over 8? It's equal to 3. So because this is to this, as 8 is to 24, and vice versa, we have proportionality. Therefore, by the converse of the triangle proportionality theorem, we therefore also have parallelism. Okay, so I hope this, like, little brief overview of this topic made sense. I encourage you to go back and rewind as needed, and then in a moment I will go ahead and move on. All right. Now I'm going to talk about using proportional relationships. This one I'm again going to hit on in brief. This is essentially word problems in context, and I did add some additional context just to kind of hit at that again. Okay, so to solve problems using similarity, we generally need to use the given information to create two similar shapes. And you're going to see that the pattern, even throughout this packet, is that they're triangles. Also, know that if two shapes are similar, they will have congruent corresponding angles, and they will have proportional corresponding sides. Okay, so here's an example. Let's say this oval here represents a lake. Okay, and PQ, this side, is the width of the lake. Now, PQ and ST, we're told, are parallel to one another. So the figure is not drawn to scale. Okay, and you should assume in general they are not. Answer the questions to find the width of the lake. So, which angle is congruent to P? T. And why are they congruent? Because they're alternate interior angles. Which angle is congruent to Q? Well, what's the other alternate interior angle? It is S. So, because this is true, we know that they have two congruent angles, so therefore they are AA similar. Okay? So the AA, Similarity Theorem. I'm going to write THM for theorem. By the AA similarity criterion, the two triangles are similar. Write a similarity statement. So here's what I'm going to do. Now this you have multiple answers for. I'm going to start with R because that's shared. R, P, Q. Okay, now we got to be careful here. Is similar to, so R is to R. Now, see how I marked it with the single and the double hatches? Now that's going to help me because single, single. T and P both have the single mark. Q and S have the double mark. So please mark this stuff up. You're always allowed to write over everything, all over it, so you might as well do that, okay? Now, suppose that PR is equal to 20 meters. Okay? I'm going to write a 20 here in blue. RT is equal to 12 meters. And ST is equal to 18 meters. Write a proportion that's going to give me the width. So what do I notice? Now, these are actually flipped around. So if you actually were to take this triangle and actually shift it over, you'd get something like this. So the P would line up like that. So what I have is this. I'm going to write it off to the side. 20 is this leg. 12 is the corresponding leg. See how they're like the side rather than the bottom? PQ is the side we don't know because that's the bottom of this one. And 18 is the bottom of the other one. Okay? The reason we say they're not drawn to scale is so that you can't say like, look, oh, but 12 is like a third of this. 18 is like a, so it's got to be, oh, 18 times 3. You don't assume things like that. Okay? So now we're gonna that's this. So now we're gonna solve it. So we cross multiply. 20 times 18 is 360. Okay? 12 times, and we should really say MPQ, the measurement. And I divide 12 by 360, and what I get is 30, and I want to make sure we have the right units, meters. Okay, good. Okay? And that's you just divide, okay? All right. So I'm going to go ahead and I'll try one more little one real quick. So the figure here is triangles ABC and DEF show a person and a tree with their shadows. Again, the figures are not drawn to scale. Okay, generally, you are not half as tall as a tree. If you are, I want to know. It must be like a baby tree or something. Like one you just got. So Jim, okay, shown by AB, is 5 feet 8 inches tall. He casts a shadow that is 6 feet 4 inches long. A tree shown by DE casts a shadow that is 19 feet long. How tall is the tree? So let's convert here. We know 19 is that 8 inches, 5 feet 8 inches. Now think about this, 5 feet 8 inches. So 8 inches, how many inches are in a foot? There's 12. So that means that AB is 5 2/3 inches, or rather feet, which is to say 17/3 feet. If I do the conversion there, that's 5 2/3. Okay, here this is 6 feet 4 inches long. So in other words, it's 6 1/3 or 19/3. Okay, so now what I know is this. Okay, for 1, I know that 17/3 is to 19/3. This is one of many proportions you can use, as x is to 19. Okay, so if I clean this up, what actually happens is when you divide 17/3, right? If I do 17/3 divided by 19/3, get this weird fraction. What is it? Well, if I math to frac this on my calculator, notice what I get is 17 over 19. So actually, what happens is the 3's cancel each other out. So what I actually have is 17 over 19, all right, is equal to x over 19. So what does that mean? 17. Okay? And Alicia, it would be a similar idea. Okay? So again, for time's sake, due to the fact that we're already hitting almost up at that 30-minute mark, I am going to move on. The other problems are very similar. You're identifying proportional information and you're going from there. Okay? So please make sure you understand anything I did here, right? And then in a moment, I will go ahead and move on. All right, so I'm going to talk about proportionality and geometric means. Again, I do have a video on this. This is one of my newest videos that I made. I'm going to go ahead and link to that. So in a moment, you're going to see something come up on the top, and I really recommend you go ahead and at some point try that video and take a look at it, because that is going to hopefully help you understand some of these problems. Okay, so in general, if a and b are numbers and x is their geometric mean, the following relationship holds. X is to a as b is to x. Or, equivalently, a is to x as x is to b. These are literally the same. You can always flip both sides, right? I could put b here and a there. Doesn't really matter. Okay, so given the triangle, and again, the video talks about this, the following geometric means apply. H is the geometric mean of x and y. A is the geometric mean of x and c, the hypotenuse, and B is the geometric mean of y and c. So an altitude is the geometric mean of the two pieces of the hypotenuse, and any leg of the big triangle is the geometric mean of the hypotenuse and the adjacent side, or the adjacent piece. In other words, whatever piece is touching that leg. So x touches A, y touches B. So A is the geometric mean of C and X. B is the geometric mean of C and Y. Again, like I said in the other video, think about it in terms of proportions and similarity, and this will be just fine. Okay, so I'm going to do one problem that's a geometric mean and one problem that involves a triangle. So one jalapeno and one habanero. So for something like finding the geometric mean of 27, I need a number such that x is to 3 as 27 is to x. The pattern you should be seeing is you're always multiplying the x's to get an x squared, okay? And then you're going to multiply, and I'm just going to get lazy here a little bit, apologies, and do 27 times 3. Okay, and then you get x equals 9. We're always, now technically we know it's plus or minus, but remember, this is representing, generally representing a measurement, so we're generally going to stick with the positive number, especially when we're in a triangle lane. If I simply ask you to solve this without any geometric mean implied, that would be one thing. If I don't specifically give you any indication to think it can't be negative, because technically, if we just saw this in a vacuum, -9 works. This is -3, this is -3. But in a land where measurements need to be positive, right, it has to be 9. Now down here, length of CD, well, that's just the geometric mean. So CD is to 8 as 2 is to CD. Okay, and I'll say measurement CD. Okay, so that is to say the measurement of CD squared is equal to 16. So the measurement of CD is equal to 4. Okay, so that's the idea behind how you do these ones. Okay, all right. So on a fundamental level, right, these are the main concepts here. What I'm going to do is I'm going to show you one proportionality problem, right? There's some nice more proportionality. I'm going to show you some one nice context problem, and then I think we'll wrap it up there. Okay, so context is this. Context, we have proportional relationships, and you just need to figure out what they are and how to use them, right? You could make them, right, fantastic beasts, proportional relationships, and how to use them. Haha. So Jimmy and John own a sandwich shop. Part of their job is to take the sandwich rolls out of the box and put them on a rack to rise. For every 15 trays they put together, a total of 105 rolls are risen. Okay? How many trays are needed to rise 322 rolls? So what's the proportion? If I want to rise 105 rolls, well, what do I need? I need 15 trays. So now, if I want to rise, well, I know the rolls I want to rise, right? What's the target rolls? Take a look. The target rolls is, well, I want to rise 322 rolls. So what I need is I need how many trays? I don't know. So I do the math, right? But we can cross multiply. So 105x equals 4330, 4830. Yep, because 32 times 1.5 is 48. 2 times, yep, perfect. All right, so 4830. Now we divide by 105. And the cool thing is, if I just have my calculator, it knows to plug in the next one, and I get 46. So in other words, 46 trays are needed. Notice, no triangles are required to solve this problem. It's just a simple matter of proportionality. Okay, so again, the point of this video is to, one, hit on all the bell pepper questions to make sure those are available to you answer-wise, and then to provide a little boilerplate for some of the problems you need to solve. For this one, I'm going to really encourage you, if you need any extra help with this, to please reach out to me. I'll be available before and after school for the rest of the week. I know that's not a long time, but again, I encourage you to take advantage of that, okay? I really believe in you. I know this has not been an easy unit, but we've shown a lot of promise, okay? And I think that if you give yourself the opportunity to do well, you're going to find yourself successful, okay? So keep trying at the content. Keep asking the questions. Keep thinking of great questions. And remember, you can do it. Okay, thanks for watching. Again, don't forget to like and subscribe so you can watch my future videos. And don't forget to love math. Have a wonderful day.